Welcome, incredible learners, to the Deep Dive. This is your essential Before AGI weekly news digest, where we try to bring you the most impactful breakthroughs in artificial intelligence each week.
That's right, cutting through the noise.
Exactly. And today, look, we're not just, skimming the surface of the cutting edge. We are diving headfirst into a development that could, well, fundamentally change how AI itself is designed.
Yeah, some are calling it a genuine AlphaGo moment for AI research, which is quite a statement.
It really is. So our mission, as always, is to take that deep dive. We're looking into the concept of artificial superintelligence for AI research specifically, this groundbreaking system called ASI-search.
ASI-search, yeah. The core idea is accelerating AI innovation way beyond current human limits. It's about shifting the whole paradigm of how we discover new AI architectures.
We spent a lot of time poring over a fascinating collection of research papers and analyses on this system, and we're ready to unpack the most important nuggets for you.
Trying to make sense of it all.
So get ready for a journey into how AI is now learning to design itself, and why this isn't just, another small step. It feels like a massive transformative shift for the entire field.
And crucially, what does this actually mean for the future, for how you'll interact with AI, whether you're, building it, using it, or just trying to keep up?
Okay, let's unpack this then. We hear constantly about how AI capabilities are exploding, right?
Oh, constantly. Feels like a new model drops every other day.
Exactly. Grok, Meta's Llama 3, Anthropic's Claude, maybe even GPT-5 just around the corner, who knows? It really feels like AI is just advancing at this exponential pace.
It certainly looks that way from the outside.
But there's a kind of paradox here, isn't there? A hidden bottleneck that's been quietly, maybe, holding back the really rapid breakthrough innovation in AI itself.
That's a great point. The core problem is this. While the AI systems seem to improve exponentially, often just by throwing more compute power at them.
Right, bigger models, more data.
The pace of AI research itself, the discovery of fundamentally new ideas, that's still linearly bounded by, well, us, by human cognitive capacity.
Think about it. We, as human researchers, we have limited time, finite brain power, and just our inherent human speed limit on innovation. We are the slow part of the process in AI advancement.
We're the rate-limiting step. Yeah.
These models we use every day, like ChatGPT, Grok, Gemini, despite how incredible they are, they're still largely human-designed, aren't they?
Absolutely. Products of human ingenuity, countless hours, brainstorming, trial and error by brilliant but still human teams.
And even though we see companies like XAI and Meta building these absolutely massive data centers, hundreds of thousands of GPUs, trying to scale AI by essentially brute force.
Throwing hardware at the problem.
Yeah. It doesn't fundamentally solve the challenge of coming up with smarter designs, does it? Smarter architectures. The limitation just shifts from raw compute power to the actual place of human innovation.
We just can't conceive of all the architectural possibilities fast enough, or even test them all, even with all that compute.
It's like having an infinite supply of building materials, but, I don't know, only a handful of architects working in slow motion.
And that's a very real, tangible constraint on the velocity of innovation in the AI field. It's not just some theoretical problem we're discussing.
Right.
For years, designing even a single state-of-the-art architecture, it could take human experts months, sometimes even a year or more, of painstaking iterative effort.
Wow, yeah.
And that process is just inherently unscalable, especially when the compute power available for training these things is growing so incredibly fast.
So the training gets faster, but the designing stays slow.
Exactly. Human researchers just cannot keep up with the potential for experimentation. We can't intuitively conceive of the vast, almost infinite architectural possibilities out there.
Which leads to the big question.
Yeah, it really raises this fundamental question. If human ingenuity is the bottleneck, what if AI could take over the design process itself? What if AI could design the next generation of AI?
That's the profound shift, isn't it? Almost sci-fi, but apparently it's happening now.
And that's where ASI-search comes in.
This is where ASI-search steps onto the scene, yeah. Offering this truly transformative vision. It stands for Artificial Superintelligence for AI Research, or ASI for AI, as they call it sometimes.
ASR for AI. Catchy.
At its heart, it's an AI system that is capable of autonomously conducting its own scientific research and designing more powerful next-generation models.
All by itself?
The researchers behind it, they talk about a fundamental paradigm shift. It moves, quote, beyond traditional neural architecture search, or NAS. You might have heard of NAS before.
Yeah, NAS has been around for a while, trying different combinations of network layers and things.
Right, but previous NAS methods, while they were helpful, they were fundamentally limited, weren't they? They were essentially just exploring spaces that humans had already defined,
Yeah.
acting more like, I don't know, selection algorithms than genuinely creative agents.
Exactly. They were picking the best option from a menu we gave them.
ASI-search, however, aims for what they call automated innovation. That means it can autonomously hypothesize novel architectural concepts, basically from scratch.
That's the key difference. It's not just optimizing within a box that humans set. It's inventing the box and what goes inside it.
To put this into perspective then, traditional NAS, even though it was powerful in its own way, was essentially optimizing within a sandbox humans created.
Right. Imagine it like trying different combinations of existing Lego bricks to build the best possible tower, maybe. It would search exhaustively through a predefined set of human-designed building blocks, trying to find the best arrangement.
Okay, so it's finding the best way to use the Legos we already have.
Precisely. ASI-search, on the other hand, isn't just rearranging the existing Legos. It's like it's inventing new types of Legos, entirely new ways to snap them together and building completely new structures we hadn't even conceived were possible.
Wow. Okay, that's a much bigger leap.
It is. Traditional NAS methods, they were restricted to those predetermined building blocks. And often they came with prohibitive computational costs for even marginal gains. They lacked, real creativity to invent something entirely new.
Just better combinations, maybe?
Mostly, yeah. In stark contrast, ASI-search can autonomously hypothesize truly novel concepts. It can implement them as actual executable code, train them, and empirically validate their performance through rigorous experimentation. And here's the kicker. It draws on both past human expertise and its own AI-generated experience.
Learning for its own work.
Exactly. This is what makes it potentially genuine scientific superintelligence. It's a self-improving, self-designing research system.
And here's where it gets really interesting, I think. The researchers draw this powerful analogy. They call this an AlphaGo moment for model architecture discovery.
Which immediately brings back memories.
Yeah, for those who might not remember or weren't following AI back then, cast your minds back to 2016. That's when Google DeepMind's AlphaGo, this AI designed to play the ancient board game Go.
Incredibly complex game.
Yeah, famously complex, way more so than chess. Staggering number of possible moves, board configurations. It needs deep pattern recognition, long-term strategy, almost an intuitive feel for the game.
People thought Go was maybe the pinnacle of human strategic intuition, almost uncrackable by AI.
Right. Many believed it was too nuanced, too human for an AI to truly master, let alone beat the world champion, Lee Sedol.
And then came Game 2.
And then came Move 37 in Game 2. AlphaGo played this move, and it just shocked everyone watching.
Total silence in the commentary booth for a bit, I remember.
It was unexpected, completely counterintuitive. At first, commentators, including top Go pros, thought it had to be a mistake, maybe a glitch.
Like, what is it doing? No human would play that.
No human would have considered it at that stage, apparently. It seemed to violate all conventional Go wisdom. But as the game unfolded,
It became clear.
Move 37 wasn't just brilliant. It was profoundly insightful. It revealed some new strategic truth about Go that went beyond human intuition. It basically dismantled Lee Sedol's strategy.
Forced him into a corner he couldn't escape. It was a moment that showed AI couldn't just master complexity, it could innovate within it, in a way humans hadn't, uncovering these beautiful truths through pure computation.
So the parallel they're drawing is?
What's truly striking here is that direct parallel. Just like AlphaGo's legendary Move 37 unveiled a beautiful truth in Go, ASI-search's AI-discovered architectures seem to demonstrate emergent design principles.
Emergent principles.
These aren't just incremental improvements. They're not just slightly better combinations of things we already knew. They seem to be qualitatively different architectural intelligence.
So genuinely new ideas.
That's the claim. These AI-discovered designs systematically surpass human-designed baselines, and they illuminate previously unknown pathways for architectural innovation. It fundamentally challenges our assumptions about design philosophy.
It forces us to think differently about how AI can be built.
Exactly. It highlights that the AI is potentially genuinely creative. It's capable of conceiving designs that are qualitatively different beyond human preconception, truly coming up with new innovations we just never thought of before.
So it's not just a smarter engineer. It's like a new kind of architect.
That's a good way to put it. A new kind of architect, with a very different way of thinking.
So, okay, how does this creative AI actually work then? This idea of an AI designing better AI. It still sounds a bit like magic or science fiction.
Well, it's definitely complex, but there's a clear framework. The ASI-RCH system is meticulously designed as a closed evolutionary loop. Think of it like a sophisticated multi-agent system that continuously improves itself.
Like a self-evolving research team?
Exactly. Tirelessly iterating, refining, making breakthroughs faster than any human team possibly could. At its core, it has four main functional modules working together: the researcher, the engineer, the analyst, and an integrated debugger.
Okay, researcher, engineer, analyst, debugger. A whole team.
A whole automated team. And if you connect this to the bigger picture, this framework mimics a highly efficient scientific workflow. Hypothesize, experiment, analyze, learn. But it's fully automated, allowing for these super rapid cycles of discovery without needing a human to step in at every stage.
Right, speeding the whole process up dramatically.
Yeah.
Let's break down those roles then. What's the researcher do?
Okay, so the researcher. You can think of this as the creative brain, the visionary of the system. Its main job is to propose truly novel architectural concepts, and critically, it doesn't just propose ideas, it implements them directly as executable code.
So it comes up with the idea and writes the program for it.
Yes, which is important. Now, where does it get inspiration? Two main sources. First, it leverages a cognition base. This is essentially a distilled library of human expertise built from nearly 100 key scientific papers, specifically on linear attention.
Why linear attention specifically?
Good question. Linear attention is a type of attention mechanism in neural networks that's generally more computationally efficient, especially for very long sequences, compared to the standard quadratic attention you find in classic transformers like, say, early GPT models. It was likely a strategic choice here because it allows for faster, more feasible experimentation on lots of different cutting-edge designs.
Okay, makes sense. So it learns from human papers. What's the other source?
Crucially, it also analyzes the system's own past experimental results. It learns from its own successes and failures, not just from what humans have already figured out.
So it builds on its own experience. How does it generate the new ideas? Is it random?
Not random, it's quite sophisticated. It uses a two-level sampling approach. First, it picks one parent architecture from the top 10 best performers it's found so far. That's the base. Then it samples 4 reference architectures from the next tier, say ranks 11 to 50.
So it builds on the best, but also pulls in some diversity from slightly less optimal ones.
Exactly. It ensures the evolution builds on proven success, but also encourages broad exploration, trying to avoid getting stuck in just one corner of the design space.
Clever.
There's also this neat dynamic summarization step. Before feeding historical data back to the researcher, a low-temperature LLM generates brief, factual summaries of the natural language descriptions of those past architectures on the fly.
On the fly, why not just store the summaries?
Because generating them dynamically each time introduces subtle variations in how the history is presented. It prevents the researcher from getting the exact same static context repeatedly, which actively encourages more varied design explorations. It's a way to nudge creativity.
That's subtle but smart. And you said it writes the code too.
Yes, and it's critical that a single unified agent handles both the architectural design and the code implementation. This avoids information gaps or implementation drift, where the final code doesn't quite match the original design idea. That's a common headache for human teams.
I can imagine. Okay, so it has an idea, writes the code. Does it just send it off for testing then?
Almost. There's one more vital step: the novelty and sanity check. Before any design goes for expensive training, another LLM evaluates if the idea is genuinely innovative. Is it just a tiny tweak of something seen before? It uses embedding-based search to check against similar past ideas.
So no cheating by just changing a variable name.
Precisely. And it also performs rigorous code-level checks, like does the design stay within subquadratic complexity, meaning will it scale reasonably or become impossibly slow with bigger inputs? Is causal masking implemented correctly?
Causal masking.
Yeah.
That's ensuring it doesn't peek ahead in the data. Right?
Yeah.
Essential for things like language models.
Absolutely vital. If a proposal fails, either the novelty check or these correctness checks, it gets rejected immediately. And importantly, detailed feedback is sent back to the agent, telling it why it failed and prompting a rewrite.
So it filters out bad or unoriginal ideas before wasting compute time on training them.
Exactly. Saves a ton of resources.
Okay, so the researcher has its brilliant checked ideas and the code. But like you said, ideas are just ideas until they're tested. How does ASI-RCH actually, run the experiments?
Right, that's where the engineer module comes in. Think of it as the system's empirical backbone. It takes those proposed architectures from the researcher and puts them through their paces. It conducts rigorous training and validation experiments in a real code environment. Theory becomes practice here.
Okay, running the actual training jobs.
Yes, but there's a key feature here that really sets ASI-RCH apart. Its self-revision mechanism. This is super important. Unlike a lot of other automated methods that might just discard a design if the training run fails or crashes.
Yeah, just mark it as a failure and move on.
ASI-Arch doesn't do that. It captures detailed error logs from any failed training run, and then it tasks the same agent that proposed the design with analyzing that feedback and fixing its own code mistakes.
Wait, so the AI debugs its own code?
Yes, it's an iterative debugging loop. This is crucial because it prevents potentially really promising ideas from being thrown away just because of a simple bug or typo. A human engineer wouldn't scrap a great blueprint for a small error, right? They'd fix it. ASI-RCH does the same.
That sounds much more efficient and less wasteful.
It really is. Plus, there's an automated quality assurance system built in. It monitors the training logs in real time. If a model is training way too slowly, say 2 or 3 times longer than similar models, or if it shows signs of fundamental bugs like the loss value behaving weirdly,
Like the learning just isn't happening properly.
the system automatically terminates that run early. It flags the issue and sends it back for revision. Again, this saves compute by not letting flawed runs continue indefinitely, and it speeds up the whole search process.
Okay, makes sense. So it trains, it debugs, it checks for efficiency.
Yeah.
Then what? How does it judge if a design is actually good?
After the quantitative evaluation, the benchmark scores, the loss values done, a separate LLM steps in for something called LLM as judge scoring.
Another LLM. Okay.
Yeah. This one provides a qualitative assessment. It judges things like architectural innovation, how complex the structure is, whether the implementation seems correct, how well it converged during training, all compared against known baselines. It uses a calibrated 1 to 10 scale.
Like giving it a report card based on more than just test scores.
Exactly. For instance, they set DeltaNet, a known linear attention baseline, at a 5 on this scale, and a more advanced version, gated DeltaNet, at a 10. This qualitative judgment is vital. It prevents the system from reward hacking.
Reward hacking? What's that?
That's when an AI figures out how to maximize a specific number, like a benchmark score, maybe in a way that isn't actually useful or doesn't lead to a genuinely better overall architecture. It games the metric.
Ah, okay. So the LLM judge ensures it's looking for true quality, not just chasing a high score.
Precisely. It ensures the system values genuinely superior, broadly useful architectures.
So we have the creative ideas from the researcher, rigorously tested, and even debugged by the engineer. But for this whole loop to be truly evolutionary, like you said, the system needs to learn from its past, right? How does it make sure all this new knowledge feeds back into the next generation of designs?
Absolutely crucial point. That's the job of the Analyst module. It's the synthesizer, the knowledge integrator. It closes the loop.
Okay, how does it do that?
It gathers everything. All the performance metrics, the training logs, the LLM judge scores, comparisons against the baseline models, everything generated by the engineer.
So it collects all the data.
Yes, and then it does something clever. To get an effect similar to an ablation study, which, for listeners, is where scientists systematically take parts out of a system to see what each part does, the analyst considers data not just from the model itself, but also from its parent and sibling nodes in the architectural phylogenetic tree.
The family tree of designs you mentioned.
Exactly. By comparing performance differences between closely related architectures, ones that differ maybe only by 1 or 2 components, the analyst can start to infer the specific contributions of individual modules or design choices. It helps figure out what made a particular design work well or fail.
That's smart. It's like comparing siblings to see which traits came from which parent.
A good analogy. And then these derived insights, along with relevant knowledge retrieved from that cognition base of human papers, are archived in a central database. This creates a persistent memory for the entire system.
The system's long-term memory.
Precisely. And this memory directly informs the researcher's next round of design proposals. So the system is constantly improving its knowledge base with fresh empirical data from its own experiments.
Okay, and where does all this knowledge live? You mentioned a database.
Right, that's the central database. It's basically a cloud-based MongoDB database. This acts as the central hub, the repository for all historical experiment results, all the performance data, the LLM scores, and those synthesized insights from the analysts.
But everything goes in there.
everything. And having it centralized and cloud-based is key because it allows numerous search processes, different instances of the researcher and engineer, to run simultaneously in parallel.
Ah, so they can scale the search process horizontally.
Exactly. Different agents can add new results or request historical data through APIs, fostering massive knowledge sharing and dramatically accelerating discovery across the entire system.
But how do they stop it from just, everyone jumping on the first good idea and ignoring other possibilities? How do they maintain diversity?
Good question. The system uses specific policies for that. For example, there's an initial cold start period. The first 200 explorations run without updating the central database. This encourages broad, unfettered exploration early on, before the system starts heavily biasing towards early successes.
So it casts a wide net first.
Right. And after that, updates happen in batches, say, every 50 new experiment results are added. This provides more stable reference sets for the researcher to draw from, rather than having the best models constantly changing with every single new result. It balances exploration and exploitation.
Okay, that makes sense. Now, with all these components, researcher, engineer, analyst, database, how does the system actually decide which designs are fittest? Which ones get to influence the next generation? Is there like a score?
Yes, there is. Governing this whole evolutionary process is the fitness function. This is the ultimate score that determines which architectures survive and propagate, influencing future designs, much like natural selection.
Okay, so how is that score calculated? Is it just the benchmark results?
It's more holistic than that. It skillfully combines both quantitative and qualitative dimensions. The quantitative part does evaluate benchmark scores and the model's final loss performance compared to baseline.
Right, the hard numbers.
But crucially, it applies a sigmoid transformation to these performance differences. So performance, think of it like a smart curve.
A sigmoid curve. Okay, what does that do?
It helps the system appreciate even small but genuine improvements in performance. It amplifies those small gains, but it also caps the influence of extreme outlier results. This prevents that reward hacking we talked about, stopping the AI from over-optimizing for one crazy score on one benchmark, perhaps at the expense of everything else. It encourages stable, robust gains.
So we're real progress, but doesn't get fooled by statistical flukes.
Exactly. And then there's the qualitative component, which we already mentioned, that score from the LLM as judge. That is seen as things like architectural innovation, complexity, implementation correctness, convergence.
The stuff that's harder to put a simple number on.
Right. The final combined fitness score is a balanced average of these parts. Fitness equals 1/3 of the sigmoid of the loss difference, plus 1/3 of the sigmoid of the benchmark difference, plus 1/3 of the LLM judge score.
Okay, so it's equally weighting loss improvement, benchmark improvement, and the qualitative assessment.
Correct. This provides a really holistic evaluation, ensuring that genuinely superior architectures, ones that are innovative, robust, and perform well, are the ones identified and propagated through the evolutionary loop. It's not just about gaming a single metric.
That sounds like a very well thought out system.
Yeah.
But it also sounds incredibly expensive. You mentioned thousands of experiments, training neural networks each time. How can they possibly conduct all this without, needing a dedicated nuclear power plant for compute?
Yeah, that's a very practical concern. This kind of closed evolutionary loop with continuous design, coding, training, evaluation, self-correction, it does sound incredibly resource intensive.
So how do they make it feasible? Especially given how huge AI models can be today.
What's ingenious here is how they manage the resources. It actually mirrors how human scientific research often works.
Yeah.
Start broad, then narrow down for the really detailed, expensive validation. ASI-search employs a clever two-stage exploration then verification strategy. This allows it to explore a vast design space efficiently without completely bankrupting the project on GPU costs.
Exploration, then verification.
Yeah.
Okay, 2 stages. What happens in the first stage?
Right, the exploration stage. The main goal here is to rapidly identify a large pool of potentially promising candidates. To do this economically, the system uses smaller models, specifically ones around only 20 million parameters.
Okay, 20 million is relatively small these days.
Relatively, yes. And it trains them on less data, about 1 billion tokens, which is also not huge by today's standards. Furthermore, for evaluation, it uses limited validation samples, maybe just 500 examples per benchmark.
So these are like quick, cheap tests, quick and dirty maybe.
That's a good way to think of it. They're designed to efficiently sift through a broad range of ideas without consuming excessive compute time or energy. This initial rapid rapid scan was still pretty extensive, though it yielded an impressive 350 promising candidates that managed to outperform the basic DeltaNet baseline.
1,350 candidates. Okay, so it finds a lot of potential ideas quickly. Then what?
Then comes the verification stage. Only the top performers from that initial exploration stage move on here. The goal now is rigorous, high-fidelity validation of the very best ideas found so far.
So they focus the expensive resources now.
Exactly. These selected architectures get scaled up to much larger models, for example, 340 million parameters, so significantly bigger. And they undergo extensive training on much larger data sets, up to 15 billion tokens.
Okay, so proper, serious training now.
Right. This two-stage approach lets ASI-RCH explore widely but cheaply at first, and then allocate its most intensive computational resources, the really heavy lifting, to thoroughly validate only the most promising candidates identified in the first stage.
That's how they get to those final, highly validated discoveries.
Precisely. It's this process that ultimately led to the discovery of those 106 novel, genuinely state-of-the-art architectures that push the boundaries. It's a very intelligent way to allocate finite resources for maximum discovery potential.
Focus the big guns on the most promising leads. Makes sense.
Yeah.
So after all this, the autonomous innovation, the self-debugging, the rigorous two-stage testing, did it actually pay off? What were the results? You said stunning.
They really are quite stunning, yeah. ASI-RCH conducted, get this, 1,773 autonomous experiments.
Wow.
Over a staggering 20,000 GPU hours, which is a lot, but maybe less than you'd think for discovering over 100 SOTA models from scratch.
Okay, so what did it find? The headline number?
The headline is clear. 106 novel, state-of-the-art linear attention architectures. And when we say state-of-the-art, we mean genuinely better than what existed before, often systematically surpassing the established human-designed baselines across key performance metrics.
Better than DeltaNet, gated DeltaNet, even things like Mamba 2.
Yes, the paper shows these AI-discovered models consistently outperform those strong baselines across various tasks, standard language modeling benchmarks, but also things like zero-shot common sense reasoning tests. And the improvements weren't just marginal. They indicated real breakthroughs in capability or efficiency.
Can you give an example? What made some of these top performers special?
Yeah, absolutely. Some of the top 5 selected for the final deep validation showcased really innovative design principles, things human researchers hadn't really conceived of in the same way. For example,
Go on.
there was Pathgate Fusion Net. This introduced a hierarchical two-stage router inside the network to intelligently balance local versus global reasoning. And crucially, it was designed in a way that ensured stable gradient flow during training, often a tricky problem.
Okay, smart routing. What else?
Content Sharp Router. This featured a gate that was content-aware, meaning it could decide where to send information based on the actual input data, and it had a learnable temperature parameter for making more decisive routing choices.
Learnable temperature.
Interesting. Then there was parallel sigmoid fusion with retention, or fusion-gated vermet for short. This one fundamentally changed the gating mechanism. Instead of the usual softmax gate, it used parallel sigmoid gates. This allowed multiple processing paths to be activated simultaneously and gave it a highly controllable memory horizon.
So different ways of controlling information flow.
Exactly. Higher GateNet used another two-stage hierarchical gate, but this one had dynamic, learnable floors to prevent critical pathways from collapsing, basically stopping important information from getting lost or diluted as it passes through the network.
Like safety nets for information.
Kind of, yeah. And finally, add a multi-path GateNet. This focused on really fine-grained token-level control using something called a unified balanced sparse gate. It included features like an epsilon floor and an entropy penalty, specifically to ensure path diversity to stop the network from getting lazy and always relying on the same processing paths.
Wow. Okay, those sound genuinely complex and novel, not just tweaking existing ideas.
That's the point that researchers emphasize. These aren't just minor variations. They represent genuinely new architectural concepts, each demonstrating AI's growing creative capability in this domain.
Which raises that bigger question again. Beyond just the impressive performance numbers, what does this tell us about how AI innovates? What are the deeper insights here?
Right. The analysis of how ASI-RCH made these discoveries reveals several really profound insights. Insights that could reshape our whole understanding of AI research going forward, pointing towards this new era of computationally scalable discovery.
Okay, like what? What's the big one?
First, and maybe the most groundbreaking, is what they call the scaling law for scientific discovery. They found empirically, by looking at the data, that the cumulative count of discovered state-of-the-art Argosoda architectures showed a strong linear relationship with the total computing hours consumed.
A linear relationship.
Yeah.
So more compute equals proportionally more discoveries?
Essentially, yes. What this implies is huge. It demonstrates that architectural breakthroughs, finding these new soda designs, can potentially be scaled computationally. It transforms research progress from something limited by human thinking speed
Our bottleneck.
to a process that's scalable with computation. In simpler terms, if you pump in more GPU hours, this system will reliably spit out more state-of-the-art ideas.
That is a monumental shift.
It really is. It means AI development could dramatically accelerate, no longer primarily bounded by human creativity or intuition, but potentially more by the availability of hardware and energy.
So the race for AGI might become less about who has the smartest humans, more about who has the biggest data centers.
That's certainly one interpretation, or at least a major factor. It could speed up progress immensely, but it also raises questions about accessibility, Who gets access to these breakthroughs if they depend so heavily on massive compute? The limitation is shifting towards compute or how long you can run this system.
A sobering thought alongside the excitement. What else did they find?
Well, it strongly reinforces that concept of emergent design principles, that AlphaGo Moment idea. The AI-discovered designs really were not expected at all by the human researchers involved.
They were genuinely surprising.
Yes, they challenged human intuition and opened up these uncharted territories for architectural innovation. It proves ASI-search seems genuinely creative, conceiving designs qualitatively different from what humans might have come up with.
So AI isn't just building on human ideas, it's actively redefining the solution space.
That seems to be the case here. It changes our role, perhaps. Maybe human researchers become more like AI design archaeologists, trying to understand and interpret these machine-generated blueprints rather than always being the primary architects.
That's a fascinating perspective. What about the complexity of the models? Did they just get bigger?
That's another crucial finding. Model complexity stability, or what you might call architectural discipline. The SOTA models discovered mostly maintain stable parameter counts, generally in the 400–600 million parameter range.
So they didn't just achieve SOTA by getting enormous.
Exactly. This is significant because it proves it was genuine architectural innovation rather than simple scaling. The system found more efficient and effective designs not just by adding more layers or parameters, the brute force approach, but by fundamentally improving the architecture itself. It shows a sophisticated understanding of design elegance, not just size.
Okay, that's important. Did it favor certain types of building blocks?
Interesting question. Looking at architectural component preferences, the system overall, across all 1,700+ experiments, showed a preference for established components like gating mechanisms and convolutions, things that are known to work well.
So it was pragmatic, using proven techniques.
Generally, yes, but here's the really insightful part. The top-performing models, the actual breakthroughs, exhibited a significantly less pronounced long-tail distribution in component usage.
Less long tail, meaning?
Meaning, while the system explored many niche or novel components during its broad search, the best models converged on a more focused core set of validated and effective techniques. It didn't just keep trying random new things for the sake of novelty in its best designs.
So it zeroed in on what really worked best.
Exactly. It mirrors how human scientists often achieve SOTA by iterating and innovating primarily upon a foundation of proven technologies, not just chasing novelty everywhere. It suggests a disciplined, effective research process, even though it's automated.
Okay, one last inside area you mentioned. Sources of ideas.
Yes, and this one is perhaps the deepest insight into the nature of AI-driven discovery, analyzing the sources of design ideas, particularly what they call the analysis breakthrough. Remember, ideas could come from three places: cognition, human papers; analysis, the system's own experimental history; or originality, new stuff generated by the model itself.
Right. Cognition, analysis, originality.
Overall, across all models, ideas came from all three. But here's the key finding. For the top-performing architectures, the SOTA ones, there was a markedly higher dependency on empirical analysis, learning from its own experiments. That accounted for 44.8% of ideas in the top models, compared to only 37.7% in the general population of explored models.
So the best models relied more heavily on learning from their own results.
Precisely. The interpretation is profound. Achieving true excellence requires a deeper, more abstract level of understanding. For an AI to produce breakthrough results, it seems it can't merely reuse past successes from human knowledge, cognition. It has to engage in that rigorous cycle of exploration, summary, and discovery based on its own experiments, analysis, to synthesize genuinely novel and superior solutions.
That feels like real understanding, not just pattern matching.
It's certainly pushing towards something that looks a lot like genuine scientific reasoning and synthesis, learning not just what works, but potentially why it works, based on its own empirical evidence. That's the hallmark of genuine scientific superintelligence.
Wow. Okay. Well, this is clearly a monumental leap forward, transforming how we even think about AI research. Like any cutting-edge work, it must have current limits, right? What are the known boundaries of ASI-RCH today?
Oh, absolutely. And the researchers are very upfront about these. These are practical constraints of current research, not necessarily fundamental flaws, but they definitely highlight areas for future work.
Okay. What's the main one?
The most significant is the focused scope. The current system only focused on linear attention architectures. As we discussed, these are generally smaller and faster, which made this whole intensive research process computationally tractable.
Right, a pragmatic choice.
But it means it's currently uncertain if the framework can be directly applied to more general or diverse architectures like, say, the massive GPT models or something like DeepSeek. The sheer computational cost of repeatedly training and evaluating models of that scale within this evolutionary loop would be immense.
So scaling it up to giant models is still a big hurdle.
A very significant research challenge, yeah. Both computationally and maybe even architecturally, the same techniques might not work as well at that scale without modification.
Any other limitations they mentioned?
Yes, a couple of others. Because running each design iteration was so resource-intensive, they weren't able to perform a fine-grained ablation study.
The thing where you take pieces out to see what they do.
Exactly. So while we know the whole framework works brilliantly together, it's harder to pinpoint precisely how much each individual module, the researcher, versus the analyst, for instance, contributed to the final success. We know the machine works, but maybe not exactly which gear is doing the most heavy lifting.
Okay, so understanding the internal contributions better is future work.
Right. And one very practical limitation for deploying these discoveries right now, the discovered architectures were not optimized with custom accelerated kernels, like using NVIDIA's Triton or similar tools.
Meaning they haven't been fine-tuned for maximum speed on actual hardware yet.
Correct. So while they are architecturally superior according to the benchmarks used, their direct real-world computational efficiency and latency in a production environment haven't been fully benchmarked. That optimization is recognized as a critical next step to make these designs truly practical and production-ready.
Okay, so we have these incredible breakthroughs, but also some clear current limitations and next steps. Given all that, what is next for this self-improving AI? Where do the researchers see it going?
They've outlined several really promising directions for future work to push ASI-RCH even further. One key area is multi-architecture initialization.
Multi-architecture.
Instead of starting the evolutionary search from just one strong baseline, like DeltaNet, they could initialize the process with a diverse portfolio of different architectures simultaneously. Think starting points from different families of models.
Ah, so seeding the evolution with more variety from the get-go.
Exactly. The hope is this could lead to the discovery of entirely new families of architectures that are even more radically different from current human designs, pushing into even more unknown territory.
That sounds exciting. What else?
They also plan to conduct that more detailed component-wise analysis of the framework itself, the ablation study, once resources permit, to better understand the interplay and individual importance of the researcher, engineer, analyst, etc., addressing that gap we just discussed.
Understanding their own tool better.
Precisely. And as we mentioned, that critical next step of engineering optimization, actually writing those custom accelerated kernels for the best discovered architectures to truly benchmark their practical efficiency and speed and prepare them for potential widespread use in real applications.
So the journey of AI designing AI, it feels like it's really just begun.
It certainly does. This feels like a foundational piece of work that opens up many new avenues.
This whole deep dive into ASI-RCH really reveals the current trajectory of AI, doesn't it?
Yeah.
We're moving beyond just building powerful tools to building tools that can build even more powerful tools autonomously.
It's a meta-level shift. AI improving AI.
Yeah. The idea that AI can not only learn, but truly innovate in ways that might surpass our own intuition, that's a profound shift for the entire field, and maybe for how we think about progress itself.
It really challenges some fundamental assumptions.
So just to quickly summarize the key takeaways we've unpacked today from this week's breakthroughs. First, AI research progress looks like it's shifting from being primarily limited by human cognitive speed to becoming computationally scalable. More compute might genuinely mean more discovery.
The scaling law, yeah.
Second, ASI-search seems to demonstrate genuine AI creativity. It's discovering entirely new architectural principles, challenging human intuition, opening these uncharted territories. The AlphaGo moment.
Emergent principles, not just optimization.
Third, these breakthroughs seem increasingly driven by the AI's own analytical synthesis of its experimental results. The analysis part, not just by recycling or optimizing existing human knowledge.
Learning from doing, essentially.
And fourth, a really positive note. The open sourcing of the framework and the discovered architectures has the potential to democratize AI research globally.
Yeah.
Smaller teams, researchers everywhere could potentially leverage these AI-generated blueprints to innovate alongside the big labs.
That's a crucial aspect, making these advances more accessible.
So we're looking at a future where AI progress could accelerate at a truly unprecedented rate, potentially leading to discoveries that are, as they say, beyond our imagination. It almost sounds, well, a little intimidating, doesn't it? This shift of core innovation from human minds to machine processes.
It can feel that way, intimidating perhaps, but maybe also incredibly liberating. It could free up human researchers to focus on grander questions, maybe more on the why and the what for of AI, rather than just the intricate how of designing the next architecture.
That's a more optimistic take. Focus on the bigger picture.
But it definitely raises important questions for all of us, for you, the listener. As AI becomes this autonomous innovator, designing systems in ways we might not even fully grasp initially, what new questions do we need to start asking? About the nature of creativity itself, about discovery, and about our own evolving role in this rapidly accelerating technological landscape. Consider how our very understanding of the word innovation might have to evolve when an AI can autonomously generate novel solutions that challenge our deepest assumptions about what's even possible. What does it mean for us, for human ingenuity, when the best new ideas are no longer exclusively human?
That is absolutely a fascinating and maybe slightly uncomfortable thought to mull over as this pace just keeps picking up. We really hope this deep dive into ASI-search has given you some clear, actionable insights into this week's whirlwind of AI developments.
Hopefully demystified it a bit.
To stay ahead of the curve and really try to be well-informed in this, let's face it, rapidly evolving world of AI, please be sure to subscribe to The Deep Dive wherever you get your podcasts.
Keep learning with us.
And hey, for even more detailed tutorials, breakdowns of tools, and other cutting-edge AI news, you have to check out Ian Ochieng AI on YouTube. That's Ochieng. He consistently does a fantastic job breaking down complex topics and tools into simple, practical insights you can actually use. Highly recommended.
Great resource.
Thanks so much for joining us for this deep dive. We'll be back next time with another stack of sources to unpack for you. Until then, keep learning.